Hello, everybody, and welcome to today's presentation. How can developers take advantage of machine learning? Brought to you by TIBCO. I would like to introduce you to our presenter, Bram Van Der Geest. Bram is a data scientist and machine learning engineer with 10 plus years of experience with software development, statistics, experiment design, and machine learning. Currently, he is a machine learning engineer and product manager at TIBCO Software, where he is in charge of integrating machine learning within the open source event-driven ecosystem of Project Flogo.
So, as Dylan said, today I'm going to be talking about how developers can take advantage of machine learning and I'm going to do it in sort of with a focus in REST APIs in general. But first, what I'm hoping that you will take away out of this webinar is sort of an idea of what machine learning is. There's a lot of hype out there and a lot of discussion, but in general, it seems like people are a little bit confused about what it is. I'm also going to talk a little bit about what is required to put machine learning in production, and it's going to include a discussion of what roles are needed. And then I'm going to give a demo about making machine learning actionable within REST APIs. Yeah. So what is machine learning? Now, machine learning is both a field and the topic of that field. Particularly, the field of machine learning is dedicated to the research, development, and application of machine learning algorithms. So to give you a little bit more of an in-depth understanding of machine learning, I'm going to define some of these terms, discuss some applications and types of machine learning, and then discuss what you need to bring machine learning to production and some of the difficulties in that deployment. Better comments. So we've all heard of machine learning, AI, neural networks, and deep learning, and a lot of people use them interchangeably. In fact, I'm probably going to use them interchangeably in this talk. However, they all have very distinct meanings that are separate from each other. So what we have here is sort of my understanding and what I feel is the definition and the overlap of these terms. Thing is, if you get 10 data scientists or machine learning engineers together in one room with this slide, you'll probably get 20 different opinions on what this is. In fact, Medium recently had an article that was had these circles all overlapping each other with AI on the outside, and machine learning, neural network, and deep learning. So there is some discussion, but hopefully this will help you understand at least some of the possible distinctions between these terms. So machine learning is focused on data and extracting insights out of that data, particularly algorithms. So whether that is fitting a line to some data or some sort of complicated deep learning network, this all relies on data to provide insight. Now, artificial intelligence is sort of the idea that a computer system can perform tasks that are based on human intelligence and or human-related activities. So this is sensing, thinking, decision-making are often examples of this. Now, neural networks is a class of both machine learning and artificial intelligence that it was originally modeled off the human brain. So basically, they're modeled off of how neurons interact within the brain. Now, neural networks uses linear algebra to interact like neurons to perform human-like tasks, whether that's computer vision, classifying text, or things like that. Now, deep learning is a subset of neural networks. You can sort of think of it as a hierarchical form of networks, so multiple layers of neural networks that are set up specifically so that the lower levels of the network are intended to learn representations of the data. So an example of this in computer vision is the pixels of an image are fed into the model, The first layer would then try to take these pixels and define lines. The next level would take these lines to define shapes. The next up from there would use shapes to define faces. And then the last level might analyze what emotions are on the faces, so that the lower levels are intended to form their own representations. And in many cases, these lower level representations can be used outside the original model. Deep learning is commonly used in computer vision, speech recognition, and NLP, but are also used in many other cases. Now, as I mentioned at the beginning, Medium has an article where AI subsumes all of machine learning. I personally have them separate because I believe that there are forms of machine learning that aren't artificial intelligence. For example, drawing lines through data is something that human beings aren't that great at, and that computers are much better at. So that's really not a form of artificial intelligence. While there are forms of artificial intelligence that are not defined around data, there are more rules-based forms of artificial intelligence. Now, generally, they don't get as much hype these days as they have historically, but they're still within the umbrella of artificial intelligence. So now that we've talked a little bit about the distinction in terms, the applications of machine learning are quite diverse. Now, here are 6 categories. However, there are many, many more categories. These are just some of the more common ones. For example, classification and regression are probably the ones you hear of most often with machine learning and AI, where classification is basically you have some input data and you want to bucket it in one way or another, trying to identify whether it is or is not spam, whether someone's running or walking, whether something detects is fraud, or any of a dozen other things. Regression, on the other hand, is basically any form of graph fitting or numerical prediction that you can do with data. So these two tend to be the most common forms of machine learning that you're going to see. However, clustering and pattern recognition are actually quite important as well, because they allow for you to discover different classes within your data, different features, and basically allow you to explore your data in additional ways that classification or regression doesn't allow. Now, dimensionality reduction is often used to prepare data for one of the other methods, because you can often start off with data sets that have hundreds, thousands, millions of columns or features that not all of them are important. So often you want to reduce those down into smaller representations, because that really speeds up other machine learning techniques. The more features you have, the more calculations are needed. And so dimensionality, excuse me, let me have some water. So dimensionality reduction can be very important when coupled with other forms of machine learning. A really interesting example of dimensionality reduction are something called word embeddings, which originally when people were doing natural language processing or text processing, they started off with just a list of all possible, say, English words. And so this can be, hundreds of thousands or millions of words. And this creates very large, very sparse matrices that have to be processed. So eventually what ended up being done is we reduced the dimensionality of these. So instead of being very large, sparse matrices, we reduce them down to a feature set of, say, 300 floats that represent the meaning of the word based on the context of what other words are around it. So there's lots of possible applications of that kind of representation. Now, outlier and anomaly detection are also commonly used for things like fraud detection, network intrusion, failure modes, also to discover trending topics. Basically, anywhere you're trying to look at something a little bit less common that is than what is extract something out of a signal that is much stronger. Now, information filtering is a combination of things like dimensionality reduction and outlier detection and clustering. But it sort of takes all three of those to represent a strong signal to noise, a strong way to remove signal to noise or increase signal to noise, help with security investigations and things like that. And as you can see, all 6 of these categories have etc. at the end, because I'm just giving a few examples that I thought of off the top of my head of the way machine learning algorithms are used. So now that we've covered a little bit of terms and some applications of machine learning, let's talk about the types. So there's 2 primary types of machine learning: supervised and unsupervised approaches. Supervised approaches rely on having input data, which I will call X here, and then learning some function that then gives a result, primarily Y, which is called labels in machine learning speak. So basically, anytime you're trying to predict an observed condition, this would be supervised learning. The problem with this is that you often need a lot of labeled data to train your model. The linear regression I have down here on the left shows that I used several hundred, well, I guess that's more like 50 points to draw a line. So for things like text classification, it can be on the order of hundreds of thousands or millions of labeled data sets, labeled comments, to be able to form a good representation of model for classification. Now, so this is one of the problems with supervised learning approaches. Now, there are subsets of supervised learning that try to minimize this. So semi-supervised learning uses a more constrained information about the system than a label for every input in training. It would be something like knowing that 10% of your data points are outliers, or some other constrained knowledge of the system. Active learning is the machine learning algorithm actually detects which samples would have the most impact of knowing what the labeled data is. This is often coupled with interactive learning, such that it would then hand this to a human being for that labeling. Then reinforcement learning is basically the Pavlov dog approach of teaching machine learning, where you either punish or reward an algorithm based on what its result is. This is often used for things like genetic algorithms. Now, unsupervised approaches are sort of the opposite of that. You don't really know what the possible outcomes are. So you don't have labeled data. You're only investigating the features. An example of this I have here on the right is clustering. So you're trying to identify where your data points cluster together and maybe identify how many clusters you're looking for, or where specific boundaries are between these clusters. So really you're looking to understand the structure of the data or uncover new phenomenon. Now, this can actually be the point of unsupervised approaches. So you really are just trying to discover what's going on. Or you can use this to feed into supervised approaches. So once you've done clustering, you see here that there's 3 clusters. So you can label it cluster 0, 1, and 2, such that you can then feed this into supervised approaches, such that that you will then have labeled data as a training set. So that's a little bit of overview of the algorithm. Now, how do we go about deploying machine learning algorithms into production? And the way a lot of businesses do that at the moment is they hire a data scientist or machine learning engineer, expecting them to build an algorithm from scratch, know which algorithms to use, combine those together with their business knowledge to create the best product possible, and then to deploy it in many cases, or to hand it off to developers. Kathy here gives a good example of why this is sort of a problem, because the people who build the algorithm have a different skill set than those who build the model. So it'd be like having an electrical engineer try to bake you bread or a chef build an oven. And So machine learning is often discussed as one field or one cluster of skill sets, when in fact it has become more obvious in the last year or so that this is actually more of a multi-layer skill set. So you have those who build the algorithms, which would usually be at big places like Google or in academia. Then you have data scientists in business sort of using the algorithms like their ovens or stoves to make new products. I'm going to go ahead and extend this metaphor that she uses and say that we actually need to worry about the rest of the kitchen, because I can make a model for myself just like I can make my own dinner. However, that doesn't really scale well when you're trying to build products. So you need people to chop and process vegetables and meat in advance before you cook. You need people to serve the results. And yes, I'm trying to make that pun there. I'm sorry if it doesn't work too well. And so this is where data engineers and developers and DevOps enter into the picture, because you really need the full suite of skills to bring a machine learning product to the world. So you need someone, maybe someone in academia who releases an open source model such that your data scientists can build off that to build their product. And then they work with developers to productionalize that. So as you can imagine, there are often problems with this handoff between data scientists and developers. Here I have a little mock conversation that might be a little short and a little bit strained, but I have had this interaction between myself and other developers, and I've seen it happen in other groups, where basically data scientists and developers not only use different programming languages, frameworks, and libraries that lead to making it difficult for models to be handed between them, and also things like data preparation, but also that they just can't communicate their needs in a easy way. And this even is pointed out by the fact that they have different success metrics. Developers are worried about stability, uptime, and things like that, while data scientists are looking at accuracy and learning rates and things like that. So some of the ways we address that, is that we try to use, so here at TIBCO, we have an open source project called Flogo, which helps developers create event-driven software. I'll talk a little bit more about it in a moment. But within this, we use TensorFlow, which is a very common machine learning open source tooling that's released by Google that is deeply integrated in the machine learning community. While there are lots and lots of machine learning tools, TensorFlow is sort of the gorilla in the room and sets a lot of standards and is very widely used. And one of the advantages of that is, or one of the things that drive it, and an advantage because of it, is that it has wrappers in many tools. So this allows us to handle some of this model transferability issues, because we can develop the code within Python and push it to Go, which is what Flogo is written in. And so even though it's written in very very low-level languages that are very quick, we have lots of possible languages that we can actually use it in, with many more added by third parties. So TensorFlow includes many machine learning algorithms that aren't really neural networks. However, it's really built to facilitate and optimize neural network work. In fact, the name TensorFlow basically is a synonym for neural network. A neuron is often represented as linear algebra, and a multi-dimensional matrix is a tensor. And then a flow is basically a graph that is directional. So that is a network. So when they say TensorFlow, they're really just saying use neural network. One of the advantages of TensorFlow is that they can also help visualize a lot of your graphs and networks with something called TensorBoard, which I have an example here. So really, TensorFlow is not the only machine learning framework that is out there, but it is a very good place to start when you're looking at neural networks. Also, it helps a lot with productionalizing of machine learning algorithms because it is somewhat language agnostic. And so from there, we're going to talk about Project Flogo. Project Flogo is set up as an open source ecosystem intended to help you write apps that are event driven. And by event driven, I mean anything from a REST API to an app that runs on an edge or IoT device that responds to sensor reading, or any of a dozen other types of events. Flogo is a very lightweight framework, much lighter than some of its competitors, Java or Node.js, and it is 100% open source. So even the machine learning aspect, which is primarily done in TensorFlow, is all open source. And some of the advantages of Flogo is that it has some common core tools that allows it to be transferred very easily from an edge device to an API. Basically, you change the initial trigger with just one quick change in the code or in the user interface, and you can completely shift your app from one environment to another. And that allows you to deploy Flogo apps as serverless functions on Lambda, within containers, on EC2, or on edge devices. And all of this is integrated with machine learning capabilities that allows you to bring data science along for the ride. So a lot of these capabilities are wrapped around contextual rules, micro gateways, integration flows, and stream processing. So all these handling of the events allows you to basically, in a linear streaming fashion, sorry, I guess I don't have that slide, in a linear streaming fashion, combine all events down together in a way that allows you to make machine learning prediction if that's what you were looking to do. And you can do it with basically no code changes. And since we have a web-based UI, a command line interface wrapped around JSON, or Flogo as a library, so you can just write raw Go code, you can do all this with very quickly with no code changes. So the machine learning capabilities within Flogo are open source and natively works with TensorFlow. It actually is set up with a generic interface that allows any framework to be integrated. At the moment, the only framework that is set up is TensorFlow, but it should be easy to extend it. And as open source code, if you do need another framework, say MXNet or Caffe, it should be fairly easy to integrate into Flogo. The way TensorFlow is set up within Flogo is we have the generic interface with some more specific code related to TensorFlow that then is wrapped around the TensorFlow Go library that reads in safe model formats in a protobuf file. Within this protobuf file it supports basically any type of neural network that TensorFlow handles. Either manually built graphs, which is what I will be doing here in the demo in a little bit, or in pre-built TensorFlow estimators, which are basically very common models that they've already built for you. And here's my pipeline graph that I thought was a little bit higher. Sorry about that. So basically, all these capabilities within machine learning or or rules-based can be integrated with the streaming pipeline such that you can aggregate your data, filter it, and make an inference. So for today, I'm going to do a very simple demo where I basically, using an API, a REST API, I send an array that contains 10 floats in the shape of a Gaussian. So here's an example where I got 10 buckets, and the Gaussian can have a peak on either side of the middle. And the very simple TensorFlow model that I have implemented determines whether that peak is on the higher half or on the lower half of the array. And it gives a result of 0 or 1 corresponding. I built a very simple convolutional neural network in TensorFlow, which I will show you the Python in which I do that. And then I export that model such that it can be read into Go code in a Flogo library, where I'll show you some of the Go code that I implement this in. And it makes it very easy to create an API. I will then demonstrate that with just a simple API post in Postman. I will have the whole API set up very quickly. I don't want to go too low, but the link here, which hopefully will reappear in a sec, and I think we're going to post to the channel, chat channel, is the all the code that I use for this demo. So first, here's the Python code that I use to build the model. So basically, all these are fairly standard Python libraries. If you install a Jupyter notebook, which is what I am currently running, with the exception of TensorFlow, which you will have to install separately. I think in Jupyter, both Matplotlib and Seaborn are already installed. So basically, I first set up some basic metaparameters and useful functions for my code. Once I've done that, basically the way TensorFlow works is you create the graph, which I've done here in the highlighted portion, and then you run it in a separate session, which is basically sort of like, once you've created the graph, let's compile it and run it, which is what is done down below. So here I create a very simple convolutional neural network where the results are basically spit out into a tensor or an array of probabilities, where it is either a probability of being in the lower half or a probability of being in the higher half. Now, this is combined with what is called the loss function, where when you are training a model in machine learning, you need to basically compare your labels or your results with your possible results, with what you are predicting. In this case, it's a form of the probability. And then you want to minimize the difference between your labels and your prediction. And then I define a prediction vector such that this is actually what is spit out when I run the model in Flogo. I then create a training step where I use something called a generalized gradient approximation to do the minimization. The atom optimizer is just a wrapper around the DZA, I believe. So at that point, I can train the model, where periodically I use an evaluation set of data, which the model has not trained on, to see how well it's doing. And you can see that the accuracy increases very quickly. In fact, if you look at the loss, plot of the loss, it drops off very quickly, and the accuracy increases quickly as well. And then I just simply save that to a directory that includes the protobuf that has all the metadata and the neural network that I need. You can also look at the network portion in plain text, which I save here, but it's really this line that creates the data that you need for Flogo. I'm not going to do it here, but you can either point Flogo at that directory or zip it, which I have done, and put it in your operating directory. So now that I've created that model, I am in the directory in which I have my Go code. And as you can see, I have created a zip file that includes my simple CNN model. From there, I will look at the Go code, which is, sorry if it's a little dense, it is standard Go. But basically what it is it's a really boilerplate main.go file, where basically there are 3 functions defined, where you one that creates the Go app, and one that creates determines which trigger, in this case an API REST call, is going to be used. So the 2 things that you would change here is what your path is in your API request, and what kind of API request you're going to use. In this case, I'm using a post. Up above, I define which port I want to use for my API, and it's called from an environmental variable. Then within this trigger, it calls a function, which is where you write all your code. And in this function, I basically have 3 variables defined. One is the location of my model, which, like I said, is right here in my directory. Which framework you're going to use for your machine learning. Like I said, at the moment, TensorFlow is the only framework we have set up. And then I define my input values from the content of the API request. Specifically, I'm going to be sending this JSON here, where I look for the input value. As you can see, it's what I am sending is a 2-dimensional array, where the first row here is one Gaussian example, and the second row is a second Gaussian example. And actually, I believe it's the same one because I accidentally dragged one over the other. I basically have to do some processing where the TensorFlow model expects this to be actually 4-dimensional. So basically, it expects 2 more brackets around each number. So I just basically quickly process that within Go, and then define that with the name of the input from the model. So if we look at our model here, which is defined here, our input is named X. Also, we have another input named Y, which is our labels, but since we're not training the data, this input is not needed. So that is just defined in a simple map where I put all 3 inputs. This is, I then call the Flogo library, where I'm looking at the machine learning activity, which in this case, we're making an inference. We're making an evaluation of the model, where the input is the map we defined above. This then gives me a prediction of whether the Gaussian has a peak in the top or bottom half of the arrays, that I then basically put into a response that is sent back from the API response. And that's basically all the Go code you need to create a machine learning API. So for an example, I'm going to go ahead and in my command line here, which I will make bigger, I define which port I'm going to use as an environmental variable. Then I'm going to go and run Go generate, which is a common Golang tool for generating metadata in large projects. Then from there, you can then build your binary. In fact, I'm not going to build a binary. I'm just going to run it as if it had already been built, which you can do in Go with just Go run and then the same files that you would use to build. So when I run that, you can see that my API and TensorFlow load up here, such that in my Postman, I can send post requests. I'm running it on my local host at the port I define, and I've created a path of Gaussian. I'm sending a post with my input as two Gaussians that I want to be labeled. I send that request. You can see in my terminal that TensorFlow reads the safe model, looks at the metadata, does some other internal things, and then makes a prediction. And this is the final output, which we can see is sent back to the API as this. And we can see from the data we sent in that the peak is actually all the way to the right. So it is, in fact, should have a value of 1 for both cases. Okay, now to go back. Yep, I believe that's the full demo. If you want more information, it is all listed here on within a repo at the within the Flogo repo in our samples directory. Okay, so if you want to get started with Flogo, you can go to flogo.ai, which I believe we are going to be sharing in the chat channel here in a moment, and you can get started and get everything you need to by going to that channel to that web page. In a more direct manner, if you want to run get and run the user interface, that is a web-based model, you can get a Docker image and run that Docker image, and it will create the GUI for you at this host or at this port, or you can use go get at GitHub to get the command line interface. For more information, you can also get all our code at Flogo. There are also some other libraries that are Flogo-CLI -lib, that kind of thing. There's also a whole repo just for user contribution that has the inference model, a lot of the triggers that are useful, and things like that. Also, if you have any questions, you can go to the Gitter channel for that we have set up for Flogo. So this is a discussion board for Flogo. There's both the main lobby and the developer channel that you can take a look at. So that is my presentation. If anyone has any questions, I would be happy to answer them.
Great. Thank you so much, Bram. We did get a few questions come in. Our first one is, can you explain the difference between data scientists that build deep learning algorithms and data scientists that use models in production?
Okay, so this would be me going back to the example of the cooks that I gave earlier, where a data scientist or machine learning engineer that builds algorithms would be, they spend a lot of their time with a large data set, and then they try to build something that works specifically for that data set. So this is often, they have a standard image library. There are several out there that they then try to create a new algorithm that optimizes the possible results from that standard library. So you'd be building a new neural network, CNN, or some new algorithm. That is a data scientist that builds models. So he's sort of your electrical engineer building the oven. The other type of data scientist is more like a chef. This is the person who, within your company, looks at all possible algorithms, or looks to see if you need an oven or a stove or a microwave to best produce the product you're looking for. So sometimes they know that you need a convolutional neural network to do image recognition or to categorize your data. But other times that requires too much time or power or computational load. So it's much better to use a linear regression that to make that same classification or regression. Hopefully that helps with that differentiation.
Great. Our next question is, you mentioned different interfaces for Project Flogo. Can you elaborate on that?
Yep. So I mentioned it quickly, but we basically have three separate ways to interact with Flogo. One is is a web-based interface that you download a Docker image that includes the web interface, and you run it on your machine, and it runs out of your localhost port 3303. And if you go there in your browser, you can actually build Flogo apps by basically just clicking on triggers and activities that you need, and build it in a very graphical way that shows the flow of your the flow of your app. You can also build Flogo apps using a command line interface, which basically you can sit down and in the same way, sort of the same way you build it in the graphical user interface, except instead of doing it graphically, you can put in a JSON, this is the trigger I want, followed by this activity. And in fact, you can export this JSON out of the user interface such that you can then modify it and then run it in the CLI. Finally, you can use Flogo in the manner I did in the demo, which is basically as a library with a couple boilerplate main pages, and modify it and write whatever Go code you want, and use the powerful Flogo library such that you can reference the 400 or 500 activities that we have in the Flogo community, with more being produced every day, or be able to reference the 150-ish, the number is growing quickly, triggers that such that you can have your app respond easily to a sensor reading or API request or something like that. So those are the three primary methods you can use to access Flogo.
Awesome. Looks like we have one more question. That question is, why is TensorFlow the only machine learning framework integrated with Flogo?
Okay. So as I mentioned at one point, there are dozens of machine learning frameworks. TensorFlow, MXNet, Caffe, PyTorch, FastAI. There's a real jockeying for position on which one's the best model to use. TensorFlow, with its being supported by Google, has a lot of backing behind it. It has a lot, it has sort of become, if not a standard, at least a strong milestone within the community. And because of this, it is actually really easy to use it across multiple languages. Since Flogo is written in Go, and one of the reasons why that is done is because it greatly reduces the footprint of the final application. TensorFlow is basically one of the few models that makes it really easy, or sorry, one of the few frameworks that makes it really easy to transfer between languages, particularly Python and Go. So that's the reason why we interface with TensorFlow first. At the moment, that's the only one in our short-term roadmap for what we're going to support. However, since it is open source, you can add whichever framework you want. And in the future, as Flogo grows, we're going to add further frameworks within this within Flogo.
Great. That looks like all the questions we have. So, Bram, is there anything you would like to add before I close things out?
No, I think I hope everyone joins the Flogo community. It's we have a lot of very helpful people active on our Gitter channel that answers a lot of our questions that exist. So I hope to see you there, and there are lots of people who do handle some of the more Flogo specific questions. I tend to answer most of the machine learning questions on those Git channels. So I hope to see you all there. Thanks.
Great. Well, I'd like to thank you, Bram, for a great presentation today. And I would also like to thank today's sponsor, TIBCO, for providing the audience with a great webinar presentation. And lastly, thank you to everyone who attended today. We hope you learned something new that will help you in your developer career. Have a great day, and we will see you next time.